Good morning, everybody. So it's my great pleasure to introduce our distinguished lecturer this year, Professor Mike Taylor of Utah State University. So as most of you know, and so I'm only saying that more for the students, the distinguished lecturer is the highest award CEDAR can award. We are a poor community, so that means our highest award is actually ask someone to give a talk, to work for us, right? That's... So we are very glad that Mike is going to do that. And so Mike receives this award for his pioneering work on optical remote sensing of Earth's air glow from the ground, from the air, and from space. So let me say a few words about Mike's background. Mike is from England, so nobody is perfect, right? So he got his PhD in atmospheric physics from Southampton University in 1986. He then moved to Logan in Utah in 91, if I counted correctly, first as a research appointment at the Space Dynamics Lab, and then later on as a tenured full professor at Utah State University. And as a professor, Mike really likes to teach. That's why we do that as faculty members. Mike has advised over 15 graduate students and uncounted undergrads, introducing them to our profession and to our field. And actually, I must say, I don't really recall being at the CEDAR meeting since I was a grad student many, many years ago without Mike really being there and sharing his excitement being an astronomer and really being an inspiration for me and I'm certain for most of us. So scientifically, I think without Mike, we wouldn't really know what we know today in our community about gravity wave dynamics and vertical wave coupling. So Mike wrote over 200 publications about small-scale wave dynamics, observations of the air glow. They have been cited almost 10,000 times, so I think that clearly shows the impact. But I only want to highlight one particular paper Mike wrote over 30 years ago. And that's because at CEDAR we talk a lot about vertical wave coupling and about dynamics, how the lower atmosphere drives the upper atmosphere. And Mike, together with Hapgood in 1988, wrote a truly groundbreaking paper that kind of paved the way of how the lower atmosphere drives upper atmosphere variability. So about the thunderstorms as a source of gravity waves in the air glow. So Mike has also made many other first discoveries throughout his career when traveling the world and pointing his camera upwards into the sky. So, and I can't really list them all here because I don't want to eat too much into Mike's lecture time here, but only to mention two. That's quantifying gravity wave occurrences, occurrence frequencies, and the role of gravity waves in bubble seeding and for spread F. And so Mike will continue to serve our community as the principal investigator of the Glow Mission, which is about to be launched to the International Space Station later this year, and from which we as a CEDAR community can really expect an amazing new view of how the lower atmosphere is driving upper atmosphere variability. So Mike, we are very much looking forward to your distinguished lecture and what one can actually do when traveling the world and pointing a camera upwards into the sky.
That was a good couple of minutes used up, but I really enjoyed them. I've never been in this position before, and I want to seriously thank everybody here and the committee for all of their support through the years. I've been coming to CEDAR meetings, nearly all of them, and have so much support and activity together. So let's not use this time up too much. I've got a lot to show actually, and I hope you enjoy it. So let's go on. Okay, Jens referred to groundbreaking research, but I started off my career finishing being a student at Southampton University in Britain, and I was a bit of a loss for a job. I did have jobs, but I didn't want them. I wanted something exciting. And lo and behold, I was leaving the department, physics department, on the Friday afternoon, feeling a little low, and I saw this little label advertising opportunities for students to become involved in space research. Well, I lit up on that, ran upstairs to the room of the lecturer who I hadn't met before, Pam Rothwell, who used to be our mentor for the rest of her career. But we talked and chatted, and she basically hired me on the spot. You could do that in those days, I think, or at least legally. And that's how I became involved with space physics, and it involved using a television camera, which came along out of the blue. Pam was very good at negotiating, and although I was actually initially making parts for sounding rockets, so that got superposed by the potential to use a camera, a very sensitive camera, which was being made available by a hospital in London. They use those cameras for basically body scanners, and you don't want to kill the patient. And but those cameras got them more safely, and they had them as they became available to us, and we started using these low light capable cameras to look at the sky at night. And that's when you discovered the gravity waves and all of the features, other emissions. It opens up the door. So that's, yeah. Good. So that's a bit of a monster there. That's our Isocon camera. That's one of the ones that was given to us. There's a small one to the right, which is another version of it. But we would carry that on trains, buses, planes, you name it. We lost it in Japan at the airport. And so it's done a lot of traveling. That's hence our title, you know. We can go anywhere you want as long as we can get there. Next slide. And look at that. This is a beautiful Matterhorn in Switzerland. We were there with that camera. Let's go to the next slide. And this is referring to some of what Jens referred to, was that on one day there with Mike Hapke, my colleague, and we could see this bright region on the horizon, and immediately think it's due to clouds. But what was keeping them lit, especially as you're getting more into twilight, it should be getting fainter. But it just kept getting brighter and brighter. And then we realized the next day, we'd seen so much here, we'd seen a bright night, which is, bright nights are occasions when the air glow emissions get much brighter. And that's what one of these are. And you see the picture on the bottom left, you see structure in it. There are structures due to gravity waves passing through this bright light like cloud layer, not cloud, but air glow layer. And on the top right, you can see a mapping of those, and it showed that it was actually related with a thunderstorm over France, several hundred kilometers away. So we were seeing there gravity waves in action, energy transport, and getting all of that information to be able to make those conclusions. And that's, let's go to the next slide. And that's emphasized here with just parts of cartoons. This one's from Colin Hines, and you can, and oh yeah, it's showing the propagation of gravity waves from their sources, as Joan showed there, Joan Alexander, propagating upwards through the troposphere and always being generated into the mesopause region. And essentially all of the things we preach and talk about today with the students, this is the way that energy can go up. And the box on the bottom right there shows what really, we still don't know how much energy is going up there, and whether it's controlling factors and bright nights, so they have any importance, and if not, you know, the door is still wide open for these things. Okay, so this shows now some of the sources. Not all of them, but just indicating the sources that we can expect to encounter when we go to interesting sites where they're being made. And this is one interesting, obviously, couldn't pack up and go and chase a Tongan volcano erupting. We had to think of that from afar, but maybe in the future we should make it so that we can go and do these things. So you really can see gravity waves of the similar scale sizes that you get from weather disturbances from these other major disturbances. Next slide. So, what are we measuring? Essentially, I've said it's the air glow emission. If you, with your astronaut glasses on, you can see that green glowing layer that is, completely surrounds the Earth. It's a natural phenomena, and it. Sorry about my throat. You can see it glowing at night. And basically this is the layer that as the gravity waves propagate up through, you can see their structures as they go up through that. Go to the next one. On the right-hand side, I've superposed some red line emissions. I'm not going to dwell on this, but the important point is there are several air glow layers completely surrounding the Earth, and they have different altitudes and brightnesses, but they're all going to be affected by gravity waves as they propagate through these layers. So we have a way of basically testing things. Let's go another step further. I'm going to be out of breath. No, a step further in terms of mobility. I didn't say, but that image of those curved waves, they really got around the world in terms of being very important for influencing progress in this. And here's an example where Doran Baker in Utah State, he saw our presentation and invited us to come to Utah to take our cameras there, set it up, and we'll drive anywhere and set up and take some data. You know, we got it, and that's what we did. That trailer there on the left, on the right, you can see some gravity waves seen by a camera with a fairly narrow field of view. Think of it it snaps up on the sky. But any gravity waves in that box, we could see them with the camera. That's the bright part. But we don't have any way of measuring its temperature or anything like that. But with this, what Doran gave us was an interferometer, a field-widened Michelson interferometer, very sensitive and built by Alan Steed at Utah State. But that instrument is the one that's sitting there pointing upwards. It was actually by the side of that. Oh, I should use this, shouldn't I? Basically, rotate that round 90 so that it points out of towards us. And here's a telescope that's attached to it with the camera. So we had the camera bore-sighted with the interferometer. They're both looking in the same direction. So we're getting temperatures and we're getting brightness values and structure. So that's a great piece of data, this, and that was another great success for us to be able to now then determine or calculate what the temperature perturbations actually were. And I haven't shown it here, that's for you to find out, but it's really quite significant, and it will drive the ones that we'll show you later in this talk. Okay. So armed with that, we're really doing very well with these instruments. It's still the old ones, but we learned that they're building new CCD cameras for other regions, and we borrowed one from Photometrics. And this is at Arecibo during the 10-day run. But essentially, we were able to use the cameras, these ones, to get more data that we could quantify with, because our camera that is from the hospital wasn't the best in the world, but it was doing well. Here we go. So this is a camera So we wanted to be more sophisticated. So we had a filter wheel with a camera. It's rotating around and takes pictures of a green line, the sodium line, the OH layer. It does that continuously rotating around during the night. So you get measurements. But what we get in this camera is, because these air glow layers occur at different altitudes, an OH layer is at different altitude to a green line layer by several kilometers. So we get information on the altitude variation and the temperature perturbations. So we've got all that extra information now just by running this new camera there. And as I said, so that was a system that we tested it on the roof here in the US, and also then deployed it to Antarctica. Let's go to the next slide. So here we go. This is showing what the camera can do. That's about 3 hours worth of data, I think. But it's showing you now, this all-sky image, it's showing you gravity waves rotating across the sky. You can see these as bright nights sometimes. We'll talk about those one day. But most of the time, whenever we look up at the sky with these cameras, it's full of gravity waves. Totally rich. In fact, and it gets to the point where you then start getting events which you'd never even thought about. This is one where I think it's doesn't matter, but I think it's on the weekend time, so we weren't all studying it. But essentially, what we had was one camera and more filters on the filter wheel. So we're getting a picture here and another one here of a different emission. So what we could see was that looks like one wave was moving one direction and the other one the opposite direction, but it's really the same wave. So we had this sort of a wave crest here and this one here, but these would be coming down this way and the other ones would be perpendicular to it. So that was eventually determined by Ed Dewan at the Air Force, and he said it's definitely a Boar. Boars are events that are well known if you sort of looking at it on lakes and things like that, and rivers, I should say. Sorry, not lakes. Anyway, they became to be very high contrast, and as you can see, measuring this gives you the temperature perturbations of one of those emissions, and the other one gives the other one. So that's really, it became famous for its strangeness, and so I got nicknamed as the Taylor Boar. So you're supposed to laugh at that, don't worry. Not too much. Anyway. Well, now we're going into, we've got a camera, it's where we want it to be, we can let it roll and take data, analyze the data. I said, now we're in Brazil. And there were nice facilities there, and we left the camera there for a couple of years, and we got some great data there. And basically, we can build up these information for different sites and times, and compare them. Are the Boars or are the waves you see in Brazil the same ones you saw at Arecibo or in Antarctica and things like that? What are the sources? Well, we think we know what the sources are. Do they show the same signature? Next one, please. Oh, a little bit of R&R. We'll put this one just to break it up a bit. But essentially, yeah, when you go on these field campaigns, and we've done several of them, lots of them. Dominique's done tons. And we have the capability now to make these measurements, I just want to say, everywhere. Next slide. And here we can see an event. So once again, these things just pop up and go across the screen, and not bad. But then you get some other ones which are really important ones. In terms of we measure their brightness variations, and by doing that we can infer the temperature and intensity of the impact on the Mesospheric region. Yeah, you go to nice places and you also come out of them as well. So this is a nice shot here. I was on this ship, Shackleton, and spent some time at Halley. We got there to get some wonderful data from there as well. So, well, we're happy. We've got all this good stuff, but are we really happy? Because we haven't got any information on the temperature or the brightness that's quantified. So we talked with Bill Pendleton at Utah State and came up with a camera design where we would actually use well-known techniques that we could integrate into the camera and giving us a way to calculate the temperature of them. So let's just roll through this. So that camera was made, oh hang on a second, that camera was made with a grant, specifically a CEDAR grant, to kick off the new millennium. Get everybody to put in proposals, what new instruments do we need for the future. And that was funded and worked well and calibrated, and so that's all the information you need when you look at it. Let's look at the next slide. And here basically it's you're looking at the emission lines from the brightness of the emission lines and taking ratios of them, and that's well developed method. John Merriweather has made that very clear. And so this camera now then can give us temperature and intensity, as well as all the other stuff. So this is getting to be really good. And you can see it's a simple relationship that we bring together to do that. Next slide. And just showing down here, so we've got the same wave event seen at different wavelengths, looking at the perturbations, taking the ratios, and coming back with the temperature perturbations. And there are you can make different ratios from different mixing. So that's very capable. So we've got now this advanced, that temperature mapper there, the AIM-TM, and we've had that on the roof at Starfire with Chet Gardner and Gary, and basically that's down in Air Force in Maui, and in Andy's LiDAR Observatory, where we have a system with the radar, with the LiDARs that are there as well. So now we're bringing these instruments together at different facilities. So we're getting even more capability. So CEDAR is growing in its capability and dealing with, just it creates a center of excellence. Next. This is an example where we have the same event, but seen by two cameras from two different places. So Steve Smith has a system giving you the large field of view. Sorry, I think I was pressing the button too long. Oh, there it is. Yeah. So we have one small field of view in colour. That's our camera, because we had intensity and temperature. And here's the field of view of the other camera, and Carlos Martinez is involved in this too. And we superpose those. And I wanted to put that up to remind that that's another parameter that you have available. You can zoom in and get higher resolution. And I know that plenty of people, Dave Fritz loves very, very small scale waves, and you can superpose them and sort of zoom in on them. Next one. So we haven't given up yet on what you can still do with these cameras. And we're calling this one the Advanced Mesospheric Temperature Mapper. What's the advanced bit about it? Well, in the time since we last bought a camera, the capabilities of some of the ones in the in-gas ones, in the infrared, are really important because they have intensity, brightness, at least 70 times that of the current camera we have. just because we're looking at a different OH emission. So it gives us more signal. So we got stronger signal. We have we talked with SDL and said, go, and that's the Space Dynamics Lab. And we have this support. It's actually from the Air Force to build this one. And this is 10 feet long. 10 feet long, it's like a bazooka. In fact, a big one. And here it is set up this is in Antarctica. We have it in several places, I want to say. Yeah, and here's our ratio method, looking at the emissions, two different emission lines in the background, always checking the background, and you then get a temperature plot, intensity plot, take the ratio, you've got your momentum flux. Okay, and here's a plot of momentum flux, or not, that's not a momentum flux. Well anyway, it shows the variability and the quality of the data, because the other thing you can, with a higher signal, we can take them at a much quicker resolution. And that's what's showing here. That's actually an image. This is called a kiogram, where you take an image and take a slice down the middle and stack it up, then put another one down the middle of the next one and stick it up. So you end up with a lot of information of how the event is proceeding. And so we have a lot of data in these kiograms. And basically this gives you a measure of studies during the course of the night. It's getting brighter, fainter, and what other structures might be in there. You can see some of these. You might show, if a bore passed through it, you'd see a sharp line here in that data. We have plenty of those. So it's a good way of archiving it. This is now looking at raw data. It's been flat fielded, but nevertheless, you can see, just watch this. You see this? So you're seeing a wave pattern which was very smooth when it first came into the field of view, breaking up completely. Oh, you're doing it again. Good. Thanks. See them there now? Oh, and here's the temperature. So we have a temperature map now as well. Here you can see those features breaking down. So now, instead of it being, we think they break up when they get big enough, and where do they come from? And when you get an image, it gives you more insight into the data. And when it happened, how big a field of view did it happen? If we had a bigger camera with a bigger field of view, we could make even more maps. And, okay, so here we are, no boundaries for us. Here at South Pole, and some items shouldn't be there, of course. But he got lost. Yeah. Anyway, yeah. Don't dwell on that. And maybe these guys got lost as well. There's a couple of students we found down there from Utah State. Didn't know that, but it was very nice to meet up with them and talk with them, and they helped us. So we have run instruments at South Pole for. How much is it, Dominique? 10 years? More than 10 years. Oh, thanks, Yu-Chan. Yeah. And this is the sort of data you get, because if you get a nice clear night, you can get 24 hours, and it can go to the next night, another 24 hours. Just keep the data rolling. And there's a lot of analyses been done then on not just gravity waves with periods of 20 minutes or 10 minutes or small periods. Here now we know when we do spectral analyses of them, you've got diurnal, semi-diurnal, 8-hour wave. It's all popping up in the data, and that's just, and they're so rich because these, I want to say this noise up and down like that is not noise, that's data. When we look at it carefully, the waves we see in here of a broad range of spectrums are being pulled out by the analysis here. So that's a beautiful set of data for long periods, gravity wave studies. or tides. Here's another example here. This one's basically, it's South Pole again, but now looking at a different event, and you see we're pulling out a different periodicity. And so sharp, you know, this is just data waiting to be had. And if you're interested, come and see us. Next one. Okay. Well, I think I've been one non-stop going, I don't believe it. But a bit more. Okay? Yeah. So, we will obviously go to a conference and things like that, and people come up to us and, you know, we'd like to put a camera here or do that or buy one. And so we have a lot of people in the community that want to do that. So they have, what we've done is we created with colleagues our Angwin, Antarctic Gravity Wave Instrument Network, where you put your camera at your facility, Rothera, Halley, South Pole, anywhere where you can have access to it. And the thing is, that access, which costs, is impossible to believe you could actually utilize that or run something like that, but those facilities exist already, they're all available. So yeah, people get the camera, put it in, and we can have campaigns that they're taking data all the time, so we end up with this very rich program giving data all the way around Antarctica. And that data, and so we can now study variability or other possibilities. Next one. And Angwin's been going on for a few years now, and we have, this is the Angwin, all of this is the Angwin workshops, but at different times. So different years. So now we're getting Angwin data, which has got a history. And people like to come to the Angwin meetings because we're all focused. And did I point at someone? Is it all right? Okay. All right. So I don't know where the next meeting is going to be, but it'll be soon. And this one's is an example of Angwin data analyses using different capabilities. Takuji Nakamura's group in Japan have developed a way of analysing these data more easily because otherwise the data is too cumbersome. And we have also built on that. And you can see here's an event where, I mean, this is happening all the time, and you're just seeing the gravity wave activity mainly this side, and then this side, and then nothing here. But you get knowledge on what's happening. Okay. So now let's have some more fun. We've been on the ground long enough. And here we are with Dave Fritz and all of our colleagues on the NASA, the G5 aircraft. And on this project, which is called, it's just a few years ago, and we flew our temperature mapper on the here. There's Dominique here. I'm somewhere there. But so the temperature mapper pointing up through the aeroplane and also sideways. We also flew two low elevation windows. So we had cameras so we'd actually get more information, not only in the zenith, but also as you look out away from the plane. So I'll show you some of that too. And everything's set up nicely there. So here's a plot. Dominique makes brilliant data plots. And this is the zenith one. And you can see Auckland Islands there. As the plane flies along and then turns, the pilot's told to turn to the left or right, it paints the sky. So we wanted to see, with the Auckland Islands, were there any waves? It's only 600 meters tall, and the bet was on that they wouldn't show any waves because those 600 meter outer mountains wouldn't be worth a dime. But when you start to do this, you see you've got these incredible bite outs where you see these waves, which are clearly related to the ones. So these are at the tropical altitude, and these are above that altitude, in the OH layer. Does that make sense? Yeah. And that's where the camera was located. There's another one we had located on the land, because the story goes here, is that the bet was on that we didn't have, that'd be wasting a flight, because there wouldn't be any decent signature. But as I've shown you, what we saw was one of the biggest events yet. And that's what we're showing next. So this is from a camera there, it's fixed on the ground, and the plane flies over it. So this is the temperature data. Can you see this? Is rolling, twisting, breaking. Jim Heck's got a ton of data on this sort of thing, but we know where it's all related to. You can see all these things twirling. Twirling sounds a bit weak, but essentially high resolution information on breaking events. And you can now here we're calculating some of the parameters. And we can calculate the momentum flux, and here we have a plot of it, because this event had a very sharp sort of trough in it, and we can sit on the ground, we are sitting there and basically seeing this thing growing and growing and breaking. And that's being shown here with the large values every now and then, but just twisting itself up and then letting go. And I showed it, the value there is 300 meters squared per second said. Aha. My, oh my. Do I need to go backwards? How much? I've got a lot of time. Okay, I'm on fine. Okay. Let's talk about ore. Now, ore, atmospheric waves experiment, is a child who was born out of all of this data we're seeing wherever you go. So let's get a way we can measure that, and do that obviously with a satellite. And so when the opportunity came to bid to do measurements using the space station, it became available, and we wrote a proposal, beautiful proposal that went in, and Jeff and Dave and some of the big guys. But really, really, it was a perfect proposal as far as I'm concerned, because it hit all the spots and showed you what you needed, and the reviewers liked it. And we've been taken now to the point through good weathers and bad weathers and things like that, but we're now looking to launch this instrument in November of this year. So this is a warning or a waving that we'll be able to show you. Oh, we'll talk about that in a minute. So here's some of the SDL guys who are very dedicated, some of the instrumentation there, and I spent 5 years working with them, just learning what went into the instrument and how to do it. They're a marvelous team. Okay. So now this is more like, let's just look at some of the data. I think Jess showed some of this a little while back. But essentially, you're in orbit. It's the ISS orbit, so you've got that's fixed, and we have ways then. So ISS will be going around and taking a map every 50 minutes or so, and just keeping going, and we're going to have that running all the time for nighttime measurements only. But essentially, we'll map out these regions. I've just put the information there many times during the day, or during the day I shouldn't say that, during the night. And that we had proposed as a 2-year mission, and that's what we're anticipating. So I said November this year, 2-year mission, and you're sitting on the ground or in your aeroplane or whatever, we have the opportunity to do coordinated, calibrated joint measurements. And so let's not waste this opportunity saying, well, don't want to do that, because it's going to be a long time before something comes along that can be done so quickly. There are other, obviously, missions, from NASA, dynamics and things like that, but this is ready. Next one. Oh, good. So we've been busy. That we're putting in here, it's just giving you information. I hadn't appreciated quite how busy we've been. I should point over here. I apologise for not moving around. But essentially, we've been very, I won't say very active, but I want to will remain so. And we'll do that by new students, offering new opportunities. All those Antarctic stations, all measurements now, and where we have other cameras and cameras from other people that are synchronized like ours, take the same sort of data, so it makes it easier to analyze the data. So we feel we're ready to tackle the data burst that we're going to get. And I started off with, all around the world. That sort of sounds a bit sort of weird. But you can see we've just marked out sites where there currently, or have been, measurements of great significance. And that's before Aura is in orbit, and then Aura's going to paint in all, where's this? All of this region between 54 degrees. I should draw it this way. So, yeah. Next one. Anyone got any ideas? Oh, and here's all the people that do all the work. And students love the programs because it gives them something to do that's very meaningful. I don't know whether to stop there now. No questions, right? I caught him out.
Okay, well thanks Mike for that fantastic talk. I really enjoyed that. And one thing it reminded me of, I remember years ago there was a conference up in Alaska where we had a bunch of modelers come up to talk about the aurora, and they did a trip out to Poker Flat and saw the aurora, and the comment that we got after that was from the modelers, they said, if we'd have actually seen what this stuff looks like, we wouldn't even try to model it. And somehow when I see your movies of the gravity waves, it feels the same way. They're just so rich and complicated that I guess there are better modelers these days. But anyway, I really enjoyed that. I really enjoyed all the history and the movies and the phenomena. So we have a little bit of time for questions from the audience. So if there are any questions.